Okay, coming up on Friday, we will be meeting in the LBC Computer Lab. On Monday, you have two things. You have your Chapter 9 and 14 quiz, so that'll be over independent means t-tests as well as chi-square tests. And you have your Chapter 9 and 14 homework due. So that consists of Chapter 9 Exercise 4. As I said, I'm giving you the estimated standard deviation for the differences between the means distribution. That's 2.92. And for chapter 14, it's exercise 2, so you just have 2 questions on this homework. So these are supposed to be done by hand. You should round to 2 decimal points. Everything should be stapled. Next Wednesday, March 15th, your lab report will be due, and you will get the details for that in class on Friday in the computer lab. And then next Friday, March 17th, is your exam. So today we're going to be talking about chi-square tests. They can be used to address different questions than we've looked at so far. So say you wanted to compare anxiety scores between men and women. What kind of test would you use? So if anxiety scores are interval or ratio data, you have 2 groups of people, men and women. It's a between subjects design, so you would use an independent means t-test. If you wanted to examine the relationship between participants' anxiety and depression scores, if anxiety and depression scores are both interval or ratio data, and they're both continuous, you want to see if they're related, you would do a correlation between those 2 things. If you wanted to compare men and women on the likelihood of having clinical depression, you have men and women as 2 different groups, but the likelihood of having clinical depression is actually a nominal variable instead of an interval or ratio variable. So this is when you could use a chi-squared test for goodness of fit. And so that's what I will be talking about for the rest of this video. So a chi-square test is used when your variables are nominal and your scores are representing frequencies. So what you do in this test is compare observed frequencies to expected frequencies. And we'll get to what that actually means. So just as you had tables to look at critical z values and critical t values, there's now a new table to look at critical chi-squared values. In your book, this is table A7 on page 441. There are 2 types of chi-square tests, the chi-square test goodness of fit and the chi-square test of independence. We're only going to worry about the chi-square test of goodness of fit right now. So the chi-square goodness of fit test is used when you have a single nominal variable and you're trying to look at different levels of this. So you could ask the question, are domestic or international students more likely to be enrolled in this class? So domestic or international student is a nominal variable. Or you could say, do more people say blue is their favorite color than say red is their favorite color, right? So favorite color is a nominal variable. So the data we would collect for these are frequencies to see how many people are domestic or international, or how many people say blue or red is their favorite color. And we would then compare the observed frequencies, which is what we get from our data, to expected frequencies. Expected frequencies are frequently equal distribution across all levels of the variable, but not always. It depends on the exact question that you're asking. So the formula for the chi-squared statistic, which you will be calculating on your own, is the observed frequency minus the expected frequency. You square those, divide by the expected frequency, and then add them up. So this is your chi-squared, right? O represents observed frequency, minus E represents expected frequency. For each individual data point, you're going to square it, then divide by the expected frequency, and then add them up. So I'll show you this calculation with an example question here. So the observed minus the expected is basically your mismatch. So how things deviate from your expected frequency. So using the example, are domestic or international students more likely to be enrolled in research methods and statistics? We'll use our class as an example. So in our class, we have 24 domestic students and 6 international students. If we're comparing it to the idea that there's an equal number of domestic and international students, we have 30 students in the class, so we would then expect there to be 15 domestic students and 15 international students if it was equally distributed, right? We would expect half for each category. But what we observed are actual data that we collected. There are 24 domestic and 6 international students. And so what we're going to do now is calculate the mismatch. We're going to take our observed and subtract our expected. So we're going to do 24 domestic students minus 15 expected. That would give us 9. For international students, 6 minus 15 would give us negative 9. So that's our mismatch. The next thing we need to do is square those values. So we do 9 squared for the domestic students, which gives us 81, and negative 9 squared for the international students also gives us 81. Now we want to correct for whatever units those are in. So we're going to divide by the value we expected, right? If our numbers were in the thousands, a mismatch of 9 is not very much. But if our numbers are closer to where we are, a mismatch of 9 can be a lot. So we take 81 and divide it by our expected value of 15, which gives us 5.4. So then the last step for calculating the chi-squared value is we have to sum these together. So we're summing the 5.4 from the domestic students and the 5.4 from the international students to give us our chi-squared value. So chi-squared value is the sum of these two numbers, 5.4 plus 5.4 equals 10.8. So right now, that doesn't necessarily do a lot for us because we need to know what our critical chi-squared value is to determine whether or not we can reject our null hypothesis. So we need to first figure out what our degrees of freedom are to look at our table to determine the correct critical chi-squared value. For the chi-squared test for goodness of fit, our degrees of freedom are the number of categories that we have minus 1. So in this example, we have 2 categories. We have domestic and international students. So we're going to take 2 categories minus 1, so that gives us 1 degree of freedom. If we were to look at our table, our chi-squared critical value table, we'll see that our chi-squared critical value is 3.84 for 1 degree of freedom. So now we're asking if our sample score of 10.8 exceeds that critical value of 3.84. Obviously it does, so we would reject the null hypothesis and say that data provides support for the hypothesis that domestic students are more likely to be in Psych 245. So the hypothesis testing steps for a chi-squared test start out similarly, that it's the same 5 steps, but the way that we go about them is differently. The first step is to define our populations and formulate our hypotheses. This is fairly different how we would describe these than some of the other ones. So population 1 for this question was people like those are in our study, and so that would be students in Psych 245. Population 2 would be students in Psych 245 who are equally likely to be domestic or international. So we were comparing this to an equal representation of both, right? Our expected values were 15 for each since there are 30 students in the class. Our null hypothesis is that the distributions are the same, meaning that the distribution of people in population 1 categories will equal the distribution across categories in population 2. And our research hypothesis was that the distributions are different, so that the distribution of people in population 1 categories will not equal the distribution across categories in population 2. Oops. Step 2, we could do our comparison distribution. So in this case, we're doing a chi-square distribution with our number of categories minus 1 degrees of freedom. So our comparison distribution for this question is a chi-square distribution with 1 degree of freedom. Using the table to determine the cutoff score, we found that our critical chi-squared value was 3.48, I think. And then we determined our sample's chi-square score using this formula where we did observed minus expected squared over expected and then summed those together. And then step 5 decided whether to reject the null hypothesis. So let's do another example question. You use 3 Disney princesses and you decide if one is more popular than the others. So you poll people and say, of these 3, Belle, Cinderella, and Jasmine, which is your favorite? You find that 40 people choose Belle, 25 people choose Cinderella, and 34 people choose Jasmine. And so you want to know, is this an equal distribution? So How well does an observed breakdown of people fit our expected breakdown? So there are 99 people in that sample. So if there was an equal distribution, if people were equally likely to pick each of the three, then you would expect 33 people to pick Belle, 33 people to pick Cinderella, and 33 people to pick Jasmine. We have one category variable with two distributions of this variable. So our first step is to divide the populations and formulate our null and research hypothesis. So population 1 is people like those in our study. Population 2 is people who are equally likely to pick Belle, Cinderella, or Jasmine as our favorite. Our null hypothesis is that the distributions are the same. So people like those in our study is the same distribution as people who are equally likely to pick Belle, Cinderella, or Jasmine as a favorite. And our research hypothesis is that the distributions are different. Our comparison distribution is going to be a chi-square distribution now with 2 degrees of freedom, because we have 3 categories. So 3 categories minus 1 gives us 2 degrees of freedom. Next, we need to determine the cutoff score using the chi-square table in our book. So if you turn to page 441 in your book to look at the chi-square table, you will see that for a 2 degrees of freedom chi-square test, your critical value is 5.992. When you look at this table, you will also notice that these are only positive. The chi-square distribution is always positive, so you never have to worry about if it's a one or two-tailed test, nor do you have to do plus or minus values. It's always positive. Step 4, we're going to determine our sample's chi-square score, so compare our observed to our expected using this formula, and then decide whether or not to reject the null hypothesis. So here's our data. So we're going to calculate our chi-squared value. So the first thing we're going to do is do observed minus expected. So we're going to do 40 minus 33 to give us our observed minus expected for Belle. Then we're going to do 25 minus 33 to give it for Cinderella, and 34 minus 33 for Jasmine. So 40 minus 33 is 7, 25 minus 33 is negative 8, and 34 minus 33 is 1. Now we need to square these values. So we're going to do 7 squared, which is going to give us 49, negative 8 squared is going to give us 64, and 1 squared is going to give us 1. Then we need to divide by our expected values. So for each of these, our expected value is 33. So we're going to do 49 divided by 33, 64 divided by 33, and 1 divided by 33. So 49 divided by 33 is going to give us a value of 1.48. 64 divided by 33 is going to give us a value of 1.94, and 0.03 divided by 33, 1 divided by 33 is going to give us a value of 0.03. Then we need to sum these up to get our chi-squared value. So our chi-squared value is 1.48 plus 1.94 plus 0.03 gives us a chi-squared value of 3.45. As we said previously, our critical chi-squared value is 5.992. So when we make the decision now to reject or fail to reject, in this case we would fail to reject the null hypothesis because our value does not exceed the critical value. So we would fail to reject the null hypothesis and say that our favorites do follow the expected distribution, essentially that people are equally likely to pick any of the 3 Disney princesses.